Start sharing a screen. Let me just briefly introduce the talk. The title is Overview of Online and Offline Reconstruction in Alice for LHC Run 3. And the speaker is David Rohr. David, you've got 25 minutes. I will take the time. Okay, you can start.
Okay, thank you. So this talk is about online and offline reconstruction of Alice in Run 3. And yeah, this is an illustration of what I'm talking about. Basically, Alice is, as you know, a dedicated heavy ion experiment. So we're looking at lead collisions. And for Run 3, we will go to continuous readout without any trigger and increase the interaction rate significantly. And this is an illustration that shows the tracks in the TPC, the time projection chamber, where just the time is scaled linearly to the Z coordinate. Therefore, it becomes a very long, basically drift volume in this illustration. And what is shown here is 2 milliseconds of data. And in the end, we want to process 20 milliseconds at once. So this will basically become much longer than it's shown here. In total, we will record 50 times more events than before, and we will not have any trigger. So we have to store all that, which means 50 times more data. And of course, the computing resources and the storage capacity doesn't scale with that. So we have to employ sophisticated online processing and compression. And we will use GPUs to speed up that processing. The data taking plan for Alice foresees that we have a counting room 1, which is in the previous container of the former DAC and the HLT. That has on the order of 200 dual socket machines that take the optical fibers from the detectors, and they will receive 3.5 terabytes per second of raw data. In the counting room 1, there's the first compression stage, which is basically zero suppression and baseline correction. And from there, it goes to the real data center, which is in a container data center on site called counting room 0 here. Which will consist of around 2,000 GPUs and plenty of processor cores, and they are connected via an InfiniBand network. And the data rate is reduced to 635 gigabytes per second in counting room 1, and this is then further processed in the counting room 0. And this is actually where the high-level compression happens. So before it's all zero suppression, and now we have more elaborate algorithms and also reconstruction calibration. And the data rate is further reduced to 100 gigabytes per second. That is stored to an on-site disk buffer here, which will have 60 petabytes of storage, which is enough to store 1 year of, well, 1 year means 2 to 3 weeks of LED data. And then from the disk buffer, it is written to tape and to tier 1, tier 2. And what we store here is what we call CTF, compressed time frame, which is basically compressed raw data and the calibration data. Okay, the Alice detector, for those who are not so familiar with it, I'm just talking about the tracking detectors in Alice and in the barrel region. There's also a forward region for muons, but I'm talking only about the barrel. So we have in the innermost part 7 layers of what we call ITS, inner tracking system, which is the silicon pixel detector. Next, going from inwards to outward, is the famous TPC with 152 pad rows. Then we have the 6 layers of transition radiation detector. This was originally made for PID, but we can also use it for tracking and in particular for TPC calibration. And the outermost layer would be 1 layer of time of flight detector, also for PID. Coming back a bit to the processing. So what I told you before was the synchronous processing. So what happens during the data taking when there's a beam in the LHC. So we have the synchronous processing, which is synchronous to data taking and writes the data to the disk buffer and then to tape. But of course, there's also time when there is no beam in the LHC, and we would like to use this data center then for the asynchronous processing, which is more or less what was offline before. And what will happen here is that we can basically read the data back from this disk buffer to the processing farm and do the final reconstruction there. And then we will write the AODs to the disk buffer. The farm itself will only process part of the data. So in parallel, the grid can also read the CTFs, the compressed timeframes from the tier. From tier 0 and tier 1 and do the processing there and then also write the AODs. And both of them have access to the CCDB, which is our conditions database. So now I told you we want to use GPUs, and the GPUs are mostly for the synchronous processing, which happens during data taking. And this is mostly dominated by the TPC. I'll come to that in a second. This is mostly TPC tracking. And we have to basically keep it up there. So TPC tracking defines the size of the farm. So we dimension the farm and the GPUs for this TPC tracking. But then you have to see that the asynchronous phase is quite different in terms of compute power, because TPC compression is done there and we have all the other detectors that now come in. So basically, if we would use the GPUs only for TPC tracking, we would waste a lot of compute power for the asynchronous processing. So basically for that reason, we have two scenarios. So baseline scenario is what we have to do. This is the mandatory processing that we have for the synchronous processing. But on top, we have an optimistic solution where we want to use the GPUs for edge as much as possible in the asynchronous phase. And the most promising part here is the full barrel tracking with all the barrel tracking detectors I just mentioned. Coming quickly to the changes from the detector. So it's not only the LHC that is upgrading the interaction rate for that LED, but also ALICE is undergoing major changes, and particularly for the TPC. So what is changing here is that we changed the TPC readout. Beforehand, we had multi-wire proportional chambers and the gating grid to suppress the ion backflow. The problem is that the gating grid can operate at some kilohertz, but this essentially limited the readout rate just from the grid without any other delays to 3 kilohertz, which is not suited to take the 50 kilohertz of data we want to do in run 3. So we are replacing the wire chambers with GEMS, gas electron multipliers, and they have an intrinsic ion backflow blocking of around 99% in the configuration we use. But of course, this still produces much more space charge than we had before in run 2, was the gating grid. So we assume that basically we have 99% suppression and a gain of 2000. So every primary ionization produces around 20 ions that drift back from the end plate to the central electrode, and they produce a space charge that goes more or less linearly with the interaction rate. And the ion drift time is around 200 milliseconds. So basically, we aggregate the ions of 200 milliseconds of data of collisions in the TPC, and the electric field produced by the ions will distort the electrons by up to 20 centimeters in radial directions, which is huge space charge distortions to the data we have in the TPC. And this must be corrected to the order of 1 millimeter, which is the intrinsic resolution of the TPC. The second problem that comes with this continuous readout is that the Z coordinate in the TPC is computed from the time of the hit and the time of the vertex. But if we have continuous readout, we don't have the time of the vertex in advance. So we have a chicken and egg problem. We have to basically do the tracking to find the vertex, but only then we can do the tracking because only then we have the vertex time. And the last change, it's obvious, I mentioned it before, we will not process events, but we will process timeframes, and one time frame for us is between 10 and 20 milliseconds of continuous data. So to summarize, the biggest challenges we have is basically the performance. So we have to process 50 times more events than before. And because we store all the raw data, all the minimum bias data, we also have to store 50 times more data than before. The calibration needs to account for the space charge distortions in the TPC that I mentioned. And then the tracking will be more complicated because it has to account for these space charge distortions as well. And it has to be able to treat a continuous readout from the TPC. So I will go through the topics now one after another. And I start with the TPC calibration. So, and I'll also only talk about the space charge distortion calibration. Of course, there's other calibrations, but this is just business as usual, like for DDX. We have different approaches for this calibration for the space charges. So the first one is track-based. And the idea here is that we basically do the tracking just as if there were no distortions, but with very relaxed cuts. So we find some tracks in the TPC, and then we match them to the outer detectors, ITS, TID, and TOF. Now we can basically ignore all the TPC information and do a full refit of the track using only the information from the outer detectors that have precise position information. And then we can compute the residuals of the hits in the TPC with this refitted track. Then we voxelize basically the TPC volume, and then for each voxel we can compute the average correction of the track to the measured TPC hit. And this gives us basically a map of corrections in the TPC. There's some more to it, technical details. This has to be smoothed and so forth, and you have to compensate for batch chambers in the TID. But okay, this is technical stuff. So the nice thing is this corrects a lot of other effects as well, like drift velocity, E+B effects, misalignment. This is all automatically corrected by that. The problem is it needs a certain number of tracks in each voxel to get correct estimation of the distortion in that voxel. And in run 2, this meant we have calibration intervals of around 40 minutes. So we aggregate data for 40 minutes and then we calibrate in that. So in run 3, we'll have much more data, so we can basically reduce this to the order of 1 minute. But now we have the problem that these distortions, they fluctuate over time. So of course they scale linearly with the luminosity or the occupancy in the TPC. This can be accounted for by just scaling the correction linearly with the luminosity. And okay, in order to be precise, you basically have a static map for 0 luminosity that accounts for some static effects, which you subtract, and then you scale only the difference between the full luminosity and the static map. But the bigger problem is that there's short-term fluctuations that come from the LHC bunch structure, that come from collision centrality and so forth. And this was not accounted for in run 2 at all, because it was not possible. But in run 3, these fluctuations, these short-term fluctuations, will be larger basically than the intrinsic TPC resolution. So we have to invent a new calibration method for that. And the idea here is a second method in the TPC that we call integration of digital currents. So what we do is we aggregate all the current that arrives at the TPC end plate. And from that, we can basically compute how many ions are produced in the readout. Then we can propagate the ions through the TPC. We can compute the space charge produced by the ions. We can compute the electric field, and then we can numerically compute the distortions. Of course, this is computationally very heavy. So in the end, we aim to apply a neural network that will just go from this integrated currents to the distortion map. The problem here is this requires the full ion history of the 200 milliseconds of drift. And this was simply not possible in run 2. Therefore, we didn't do this in run 2 because in run 2 we had triggered readout, so we couldn't have the full history. Also, this can only correct for the space charge distortions, but not for the other effects like E cross B and so forth. So in the end, we want to employ some kind of combination of these methods, where we use this to correct for the short-term fluctuations, but we use the track-based method for all the other corrections. And just to mention, there's a third alternative solution, which is kind of a self-contained thing. Instead of using these digital currents, one could also try to use cluster-to-track residuals in the TPC, basically on short-term basis. So we use, again, the track-based method globally with ITS-TRD to get a global correction, and then we do local corrections on top using TPC-only cluster-to-track residuals. But this is still under study. The procedure we foresee right now is basically that we do the first, so these two steps that I mentioned, so the track-based calibration and the integration of digital currents, we do this online. So beforehand, in run 1 and 2, we had basically 4 processing phases over the data. The first was basically HLT, then we had 2 calibration phases and then the physics pass. And now we want to basically integrate what I discussed here in the online phase, so the synchronous processing, and then we have only the second asynchronous processing afterwards. And for the TPC, we will run these 2 calibrations. So the track-based will correct for the global distortions and for all other static effects. And then we use this integration of digital currents to correct on top of that for the fluctuations of the distortions as compared to the average distortions. Okay, next topic after the calibration is the data compression. So as I mentioned before, we have to store 50 times more data, so we have to reduce the data volume significantly. And I'll talk again mostly about the TPC because this is the largest contributor to the data volume. So we use basically a sequence of multiple steps to compress the data. So we start with clusterizing the raw data to clusters. Then we use some custom data format, either integer or floating point, with exactly as many bits as we need to represent the TPC intrinsic resolution. And then we reduce the entropy of these data. There's different things we can do for different properties of the clusters. So clusters that are attached to tracks, we can store as residuals with respect to the extrapolated track trajectory. This was presented, I think, last year at Connecting the Dots, so I'm not going in detail. There's just an illustration here. For the unattached clusters, we can sort them and store them as differences with respect to the previous clusters instead of absolute positions, so this reduces the entropy, and we can store correlated values together. All the idea here is just to reduce the entropy for better entropy compression later on. The next stage is to remove clusters that are not used for physics. So there are examples here in this, so here there's an in display, and then you see several candidates that we want to remove. I'm not going into details here, but yeah, basically this is tracks that will be rejected for physics analysis anyway, so we can remove them already before we store the data, so we save the space. And there's 2 strategies to remove that. So the strategy A is, our baseline is to do a positive identification of these cases and then just remove them. The strategy B is to do identification of good tracks and remove everything else. So basically what we remove in strategy B by design encompasses everything that we would remove in strategy A, but it's much more dangerous because if we don't find a good track, we would remove it. So therefore this is only a fallback scenario, and we would aim for strategy A. And then the final step is entropy compression of the clusters using ANS encoding. And just to give you the order of magnitude, the idea is that we reduce the TPC data size from the 3.4 terabyte that comes in raw data to 70 gigabytes that goes to storage using these algorithms. And we use also compression for other detectors, but not as sophisticated because they're simply not so much contribution to the total data. Okay, coming to TPC tracking. So there's basically two things that affect the TPC tracking that comes from this continuous readout. So the first is, we don't know basically the Z position of the clusters. And we have to apply a lot of corrections for these clusters, like these space charge corrections that I mentioned before. But this we can only do once we know the Z position. And we have multiple vertices in the TPC drift time and at different times. So there's the naive brute force approach that would be just we correct all clusters for all possible vertices, and then we run the tracking multiple times for each vertex. But this would need a lot of memory and also blow up the processing time by factors. So this is basically not feasible, and we need a better approach. So I'm quickly discussing about how we do the tracking. I showed this before, so I just go through it very, very briefly. So we have a TPC detector, which means we have a vertex, we have charge deposited in the TPC, and then this drifts towards the end plates. The problem is that we can basically not know what is the absolute Z position, but we can shift this force and back in time, which means we shifted force and back in Z. And then we have these corrections that depend on the Z, so we can only apply them once we know the Z. So the idea is we have to find the vertex first. And we do this by doing individual standalone tracking in TPC and ITS. And in TPC, we just assume that we just scale everything linearly from time to Z. And we assume there's no distortions because we can't correct for them anyway. But because these distortions and the other effects are smooth, basically the track following will still work. The idea is then that we can extrapolate the track seeds that we find to the beamline. And we just assume the track is primary. And if we assume the track is primary, we can basically assume it comes from Z more or less equals 0. This gives us an idea of what is the Z position of the cluster. And then we can apply all the corrections for this approximate Z position. And we can do a refit with that. And then we can take tracks in the ITS. And then we just take all the TPC tracks that have a compatible time to this ITS track and try to match that TPC track to the ITS. And once we have matched the TPC tracks to the inner tracking, we have fixed the time of the TPC, and we can do the full refit and also to fit the extrapolation to the outer detectors. So that is the idea. And the trick here is that we basically don't do the tracking multiple times. We do it only once, but we do it in this uncorrected coordinate system for the seeding, and then we match to ITS, and then we go on. And this time we don't. This way we don't have to do it multiple times. There's a second, more subtle problem. So we need not only the correction of the distortions, but we need also kind of inverse correction, because once we have found the seed and we have fixed the Z, we want to extrapolate the track further. But now we have the track in the corrected coordinate system, but all the clusters are still in the uncorrected coordinate system. So basically, in order to do the track following, we have the track position, then we have to uncorrect the track to search for the closest cluster. Then we have to correct that cluster, and then we continue the track following. This is technical, complicated, but really it's a problem that we had. Okay, so now for the processing requirements, just to summarize what I said here, what we have to do during the synchronous processing is TPC compression and calibration. For compression, we have to process the full data, and we have to do the full tracking for this track model compression and the removal of clusters. While calibration will process only a small subset of events, and here we use events with low centrality, because basically this makes the job easier. But this means the TPC tracking is the dominant part of the synchronous processing, because the other detectors will process only a small fraction of the data. While for the asynchronous processing, actually the other detectors are dominating, because you have to see for the TPC, we did the compression already, and we also removed a lot of clusters. So actually TPC tracking is faster in the asynchronous than it is during the synchronous. Okay, then here, I showed this before, this is just an update. This is the current status of our barrel tracking chain. It just indicates which of the blocks belong to the synchronous or the asynchronous reconstruction and what is the status here. And if you just look at those with the white labels, which is the synchronous reconstruction, you see that most of them are green, and green means it's ready to be deployed. And okay, we have to progress here because basically next year, okay, we have to see with COVID-19, but next year this should go in operation. So all the white things have to go white very, very soon. Okay, then just very quickly, an important thing is that our idea is to process everything on one GPU at once. Everything means one full time frame. And the idea is to not split the time frame in sub-slices, because that would incur data transfer force and back and treating the overlaps, which means one time frame has to fit on the GPU. So we have to make sure that basically the memory fits. And for this, we have written a custom GPU memory allocator that allocates all the memory of the GPU and then just distributes it to the individual steps as needed. And we split the memory in two parts. So a persistent part on the left, this is data that is needed for following steps. And then we have the non-persisting part for input, for instance, on the right. And then we can see, if I just go through this animation over time, how different steps are running. And you see on the left side here, more and more data becomes aggregated, but the data on the right side is basically removed and replaced. And in this way, we fit in the GPU memory. What you see here is the amount of memory that we need on the GPU for the different steps. And this always includes the memory that is in this persistent store from before. So basically what we need is the maximum of this and not the sum. And with that, you see that we fit in a 16 gigabytes of GPU memory for a time frame of 128 LHC orbits, which corresponds to 10 milliseconds. If we want to go for longer time frames, we would need more GPU memory. Okay, the final plots will be on performance. So this is TPC processing only, but as I said, for the synchronous processing, this is the relevant thing because the other detectors are a very small contribution. So far, we don't have this memory management fully implemented. So at some phases, we are not reusing the memory, which means we cannot process a full time frame on the GPU yet. And what this figure shows you is the processing time estimated for a full time frame by just scaling linearly with the number of clusters. And on the x-axis, you see the number of clusters that are used for the extrapolation. And we have this for CPU, single core on the left, and for GPU on the right. And this basically means if the curve is flat, we do not depend, we depend exactly linearly on the input data size. And this is what we need. Because if we wouldn't be linear with the input data, then basically processing 2 times half a time frame would be faster than a full time frame at once, and this would not be reasonable for us. But so fortunately, all these curves look very flat after some onset. So for the GPU, you see we need at least like 6 million clusters, but this is simply, we need these many clusters to have proper parallelization on the GPU. But as soon as we have a certain minimum data size, the processing basically depends just linearly on the input data size. It doesn't matter how long the time frame is, we can just process this at once on the GPU if we have enough memory. So next slide shows some performance measurements. So the first table gives an overview of the different processing steps we have on different GPUs. So one AMD, one NVIDIA, and for comparison also an Intel Skylake processor. So I'm just using one core of the processor. You can, I mean, if you have 10 cores, you just divide it by 10 because it can run in parallel. Just to mention here, most of the steps run reasonably efficient on the processor, except for the cluster finding, because the cluster finding is an algorithm really developed for the GPU. So the speed up of 270 between the GPU and the single processor core for the cluster finding, I wouldn't take that for real. If we would run that on a processor, we would develop a different algorithm. But for the others, it should be more or less what we get. And we see that if I take the asynchronous processing here as an example, which is I think more relevant because it doesn't include the cluster finding, then one GPU can replace 56 processor cores. So this shows that we can really save money by using GPUs. Okay, and on the lower part here, I have some more GPU models. So this is just the performance of the GPU model relative to the NVIDIA 2080 Ti GPU. And so looking at this for us, basically there's 2 GPU architectures that look promising. So one is NVIDIA Turing. So this is the 2080 Ti, which is the gaming version, or the Quadro RTX 6000, which is the professional version. And then the same for the AMD Radeon 7 and MI50, which is the gaming and professional version of the Vega 20 chip. So the NVIDIA card looks a bit faster, but the AMD card is a bit cheaper. So basically we have to see in the end what is the best price performance that we can get. Basically we have to consider the total cost of ownership here. And then, of course, also factor in stuff like support and so forth. Okay, coming to my summary. So Alice will record 50 kilohertz of LED data, only minimum bias data in Run 3. So we store all the data that we get. And we will not take events, but timeframes of 10 to 20 milliseconds. We need to employ sophisticated data compression to store all this data because the storage size doesn't increase with the data rate, of course. And we have an online processing farm on site that is also used for asynchronous processing while there is no beam in the LHC. Usage of GPUs is mandatory to keep up with the data rate in the synchronous phase, and we aim to use the GPUs also for the asynchronous processing. The most demanding calibration things are for the TPC space charge distortion. Here we have 2 approaches which we have to combine, so the track-based calibration and the integration of digital currents. And we have to adapt the tracking algorithm to use these corrections for the space charge, and also to account for the continuous readout. For the data compression, we have to reduce the total data size from 3.4 terabytes per second to order of 70 gigabytes per second that is written to a disk. So this is TPC data. On top comes around 20 gigabytes from other detectors. And we employ an improved version of the Run 2 compression for that. The plan is to process a full time frame at once on a GPU. And for that, we estimate that we need 16 gigabytes of GPU memory to process 10 millisecond time frames. A 10 millisecond time frame would mean we lose 1% of statistics at the end of the time frame. And then we evaluated many GPU models, and the most promising one seems to be the RTX 2080 Ti or the AMD MI50 and this NVIDIA card. So one GPU would replace roughly 56 processor cores. Thanks for the attention.
Thank you very much, David, for this very complete overview of the LHC Run 3 processing system. We've time for questions. Please use the raise hand feature. Let me go first. I mean, I was wondering when you talked about the space charge of the gems, how large the effects are which you are expecting, because I mean I'm sure there are some test beam results. Do you know by chance how big these effects will be, and if that could become a problem?
No, I mean the space charge is certainly sorry. What problem?
If it could become a problem for the processing chain if these space charge corrections are too large.
Yeah, so basically the 20 centimeter distortions in radial directions is the absolute maximum that basically if we put in the worst case estimate everywhere. In R5 directions, it's less. And then you have to see this is also only for the full drift, so for the electrons that come from the central electrode, more or less, because they have most distortions because they drift for the longest time. There's some factors which we don't fully know yet. For instance, the electron drift velocity is quite well understood in the gas, but the ion drift velocity is not. And of course, the drift velocity of the ion scales linearly more or less with the number of ions that is in the volume. Yeah, so I mean, what we know is that if these calibration procedures work, we can correct for them. Basically, this is simulated, and this we know from Run 2 data. And this track-based compression certainly works because we employed the same for the Run 2 data. A bit more question mark is for this digital current-based correction. I mean, it's clear that you can do it numerically. The question is still how well can the neural network approximate the numerical results? And what is also not so far, we applied the neural network to go from the space charge map to the correction map, and that works. But what is a bit missing is the step to go from really the currents that are measured at the end plates to the space charge map. And here we don't have good measurements because basically the test beams don't give us the data as we have it in Run 3, because basically the occupancy is much lower than we will have in Run 3.
So the build-up is smaller.
Yeah.
Yeah. Okay. Since I don't see any other raised hand, you mentioned that you're not able yet because of the memory management to process a full time frame in the GPU. Could you give a bit more information on how critical this is for finishing up the system? Is there a technology problem behind it, or is it just work in progress?
The problem is that this memory reuse here is not working as smoothly as it's shown here. So in some places we allocate memory here in this right part and we don't free it anymore, so it cannot be used by further. So this is just a technical thing that needs to be fixed. I would say the timescale to fix that is on the order of 2 months from now, because this is really urgent for us. Absolute worst case, if we run out of memory, is we could slightly reduce the time frame length further. So if we use, say, 8 milliseconds instead of 10, the problem is that at the end of one time frame, we lose one drift time of TPC in terms of statistics, because we don't try to reclaim the overlap between time frames. And the drift time is 90 microseconds. So for the 10 milliseconds, we are at like 0.9% statistics loss. If we go for shorter time frames, then this would increase to 1.1, 1.2%. I mean, this would not be the end of the experiment, but of course it's not nice. Yeah,
of course. Okay. Okay, very good. I think we close the talk here. Thank you very much again. I don't see any